All right, we're into our third video now for section 12.6. We've talked about some of the other quadric sections as well as cylinders. Now we're going to talk about this thing which is called a hyperbolic paraboloid. And as you might assume by the name, it's going to have pieces of it which are hyperbolas, pieces of it which are going to be made up of parabolas. And it says here these are difficult to draw, and they are. It says we'll do our best. I'm not even going to try. You can give it your best shot if you want to. See if you can sketch what this thing looks like. The one thing I am going to do, however, is I'm going to sketch the traces for us. And then I'm going to cheat a little bit because I already have a nice drawing of this, which I didn't actually draw. It was kind of a computer thing. So, so the criteria, one variable is to the first degree, as you can see in our case, the z is, and the other two are squared and have opposite signs. So you're going to have one positive and one negative. And hopefully you can kind of see how that's going to create the hyperbola part. So let's go ahead and take a look at the traces. So if we do the xy plane, so we let z equal some positive constant, like 1 or 2 or 7 or whatever it is, you're going to get a hyperbola. And then obviously depending, z is typically going to be 1 if it's a hyperbola. You could have x squared and y squared divided by things which will give you the different x and y intercepts or asymptotes or whatever, but typically in the form of a hyperbola, z would be 1. But in any case, what it would look like is something like this on the xy plane. Then you're going to have, let's just go with the xz plane. Well, basically eliminating the y there, z equals x squared is going to be a parabola which opens up on the z-axis. And then if you look finally at the yz plane, well, then getting rid of the x part, the x squared part, you're going to have z equals negative y squared. Well, that's just a parabola that opens down. It's going to look something like this. So now the question is, how do we put all that stuff together? So you're going to have something which has a parabola part which opens up, another part of the parabola which opens down. Looks like they all kind of meet at the origin. And then in the xy plane, you've got hyperbolas. So we're going to take a look at what this thing looks like. And as I said, I already made a copy of it, and here it is. There it is. So if you look at it, if you're actually really thinking about it, this thing kind of looks like something that you might see in a grocery store. As a matter of fact, it is and looks just like a Pringle chip. Pringles are actually hyperbolic paraboloids in design, believe it or not. But now let's go ahead and actually take a look at all the pieces that we had, and we'll actually show that what we just sketched actually makes sense. So hopefully what you can see is, I'm going to do my best to sketch this. Let me use the red, I guess, to do this, is that you can see the parabola part on the xz plane. So here's x, here's z, just in case you couldn't see those. So here is the parabola right here that comes down. It goes to the origin, which I know you can't really see there, so I'll dot it. And then it comes up that side right there. So there's the parabola in the xz plane. Okay. We also have a parabola in the YZ plane. It looks like I accidentally covered up my Y when I imported the picture. So we also have a parabola in the YZ plane. So in the YZ plane, it looks like it starts down here, goes up towards the origin, and then it comes back down that side right there. So there is your parabola, which is in the YZ plane. And then in the XY plane, a little bit more difficult to see this one, the way this thing is laid out, but you do have, see what color to use. I'll actually just go with black, I guess. In the XY plane, you do actually have your hyperbolas. Again, this one's much more difficult to see, but basically It's these pieces right here. I don't know how to trace this the best. This is really difficult to see, but it actually does this in both directions. This side's going to be really difficult to do. Something like that, I guess. So you can kind of see that trace. That one's a little bit more challenging. If I could rotate this, it would be better. And it's probably something I can show you guys at some other point. But this is why it is so difficult to draw. It's very, very hard to draw this thing with any kind of real spatial dimension to it. So this was done in CalcPlot 3D. That's where I put this one. Anyway, there is the hyperbolic paraboloid, one of the coolest looking ones, and it's actually going to come back up because it's got some very special features to it. But for right now, you need to know that two of the variables are squared. They're opposite in sign. The third one is has raised to only the first power. That's going to create a hyperbolic paraboloid. Now you kind of know what they look like. Just think of a Pringle chip, probably the easiest. All right. Let's move on to something which is slightly easier to deal with. It's called a hyperboloid. Again, by the name, you would think, okay, it's got to do something with a hyperbola, and you'd be right. So a hyperboloid is going to have all three variables squared. Two of the variables are going to share the same sign. So one sheet, there's two different versions. You can have a one-sheet hyperboloid and a two-sheet hyperboloid. In a one-sheet, there's one minus sign. That's the one we're getting ready to do. In a two-sheet, there's two minus signs, so they will have two negative signs. One way or the other, you're going to have one of one positive or negative and two of the other. So it's either going to be one positive, two negative, or one negative, two positive. That's the way you're going to be able to tell a hyperboloid. So let's see kind of what we got going on here. Let's say that z equals 0. If we let z equal 0, we get x squared plus y squared equals 1. X squared plus y squared equals 1, which is just a circle. So let's say z is plus or minus 1. Well, if z is positive or negative 1, plugging a positive or negative 1 in there gives you 1. Adding 1 to both sides gives you 2. So you would get x squared plus y squared equals 2. And again, both of these things are circles. First one has a radius of 1. Second one has a radius of square root of 2. So now let's do the same general idea, but with x and y. So let's say that x is 0. If x is 0, well, then we get a hyperbola. What you would get is y squared minus z squared equals 1. That's a hyperbola. What if y equals 0? Y equals 0, you would get x squared minus z squared equals 1. Also a hyperbola. So what you ultimately have here is you have in the z direction, it's creating traces upon the xy plane as circles. So let's go ahead and sketch our three-dimensional plane over here. So here's x, y, and z. And we said that if z equals 0, that's actually on the xy plane. We get a circle of radius 1. Circle of radius 1. If z equals 1, now we get a circle of radius square root of 2. So it should be slightly bigger in both directions. Something like that. That bottom one is awful. Let's try that again. Wasn't much better, but whatever. Then if we let x equal 0, so the trace of this thing in the yz plane is going to be a hyperbola. So in the yz direction, this is going to be very difficult to draw like this, but it's going to look something like this. And then it's got to also look like that on the other side. Bad start. It's going to go behind there, hit there, come out that direction, something like that. This is awful, by the way. I'm not doing a really good job here. I did say it was slightly easier. but that's a little bit better, but not great. But you'll see why I said that in a second, because it's much easier to actually draw this when you're not trying to do the traces. And then it's supposed to do the exact same thing in the XZ plane, so it's going to look something like that, and then over there on the other side, something like that. Ultimately, the easiest way to draw something like this, once again, is not to draw it by using the traces, but by understanding that the shape of it is like this. Something like that. So it kind of looks like a vase with two ends on it or something like that. But notice how it's all connected. It's one big hyperboloid in this case. This is a one-sheet hyperboloid. And again, that's because two of the signs were positive, one was negative. So it has one minus sign. One sheet. Oh, that actually should say one, not on. One minus sign. So that's the one that we have right there. So this is a hyperboloid of one sheet. And that's because the whole thing is connected. So it's really just one of them. All right, so now let's go down here. And this is pretty much the exact same idea. What you should, again, be able to tell is that I've got two positive squares, one negative square. It will be a hyperboloid of one sheet. And the fact that this one specifically equals 16 just means that my inner circle is going to have a radius of 4 on the XY plane. Still varies up and down the Z axis because of the fact that Z is the negative value. So if we were just to sketch this one real quick, you could just make this a radius of 4. You could actually just write that that's 4 or something like that. And then we're just going to sketch the rest of the hyperboloid to the edges. And we'll create the rest of it just by doing circles on the bottom and the top. So that is your hyperboloid of one sheet. Okay, let's look at one that looks extremely similar, but notice how the last one said exactly the same thing, but equals 16. This one says equals 0. Well, let's actually take a look at that one. This has a little bit more interesting stuff, because now, if Z equals 0, that means I get x squared plus y squared equals 0. Well, that's a circle, but it's a circle with a radius of 0, so it's really just a point at the origin. Once again, if Z equals plus or minus 1, we then get x squared plus y squared equals 1. So it's a circle of radius 1. Now the more interesting part. What if x equals 0? Well, if x equals 0, what you get is y squared minus z squared equals 0. That's not a hyperbola. So what you get is y squared minus z squared equals 0. If we add z to both sides and then take the square root, really what you get is just that y equals z. And if we do exactly the same type of idea with y equaling 0, well, that means you get x squared minus z squared equals 0. X squared then equals z squared, or x equals z. And both y equals z and x equals z are linear. They're lines. So when I go to sketch this, again, I have a point right at the origin. But then it looks like as I go up and down either way on the origin, I just have bigger and bigger circles. But what connects those circles are linear. Okay, the XZ plane and the YZ plane are going to be made up of lines. So what this thing actually forms is a cone, where every possible circle up and down is created by this stuff right here. Those are what's going to form your circles. And these pieces are the linear outside. So really what you get is a cone. It still technically is a hyperboloid of one sheet, but it's also just a cone. So this is also a one sheet hyperboloid. But because of the fact that the constant there was 0, we get a cone. All right. All right, just a couple more quick examples. Because the one thing I have not shown you yet was the two-sheet hyperboloid. So, the one thing you might look at and say, well, wait a minute, you said that two of the squares have to be negatives, and that's true. Look at the right side, however. The right side says that it equals -1. Well, that doesn't make sense. So we're going to divide both sides by a negative, in which case now we get -x squared minus y squared plus z squared equals +1. Now I have two negative squares. And really what you want to do is you want to factor that negative out of those two terms to make it a little bit easier to see. So, once again, to figure out kind of what the traces look like, if z is 0, well, if z is 0, what that really gives you is x squared plus y squared equals -1. Well, that doesn't make any sense. That's trying to tell me I have a circle with a radius of the square root of -1, which basically means there's no value at 0. For z equals 0, there's no value. As a matter of fact, you won't get a value until z is greater than or equal to 1, or z is less than or equal to -1. So when we graph it, z cannot start until it gets to +1 or -1. After that, it's going to look just like a hyperboloid would. So, if we sketch it, it's going to look something like this up here, and then it's going to look something like this down here. So this would be at 1, this would be at -1. Let me go ahead and extend the z-axis down so you can see that that's exactly what that would do. This would be a hyperboloid of two sheets. And again, it's because you have two separate pieces that create this thing. So this is really only going to be the case when you have two of the squares negative and one positive. That's when you're going to get a hyperboloid of two sheets. All right, last example. This one's going to go really quickly. It's really just going to be, let's see, that's going to be a hyperboloid of one sheet because I've got two squares and one negative. Biggest thing about this one is that it is not going to have circular traces. It's going to have elliptical traces. Okay, not really anything that we have to stress too much over, but if you were to let z equal 0, so by the way, the one negative is the y, so that's going to mean that this thing is going to elongate along the y-axis or circle the y-axis or ellipse the y-axis, I guess you would say, because these technically aren't circles. So in this case, if we let z equal 0, we're going to get an ellipse that looks like the x-intercepts are going to be at 2 and -2, and the y-intercepts there won't be any y-intercepts. That's right, because that's the hyperbola part. It's if you let y equal 0, I apologize. Then you're going to get the x-intercepts of 2 and -2, z-intercepts of 4 and -4. So 1, 2, 3, 4, 1, 2, 3, 4. And then the z, I'm sorry, that was the z. The x is going to be 2 in both directions. So it looks like your trace looks something like that. And then it's going to extend along the y-axis and just keep getting bigger. So it looks like it's going to be something that looks like this, and something that looks, whoops, kind of missed like that. It's going to have a little elliptical shape around the y-axis. Not the best sketch there, but at least you get the idea. All right, that's plenty enough. That is 3 videos. So hopefully you'll be able to figure out your quadric surfaces and your cylinders from this.